All right, line P1, learning task number 4. We're just going to talk about transformer builds and markings and ratings. And there's just a lot of stuff that comes off the nameplate that we need to kind of cover over and what the purposes of them are. We do know what a transformer is already. It's a component that is made up of turns of wire that are going to go and concentrate magnetic lines of flux into a core, and they're going to allow us to pass electricity as magnetism from one circuit over to another. We should have, in most cases, excuse me, we should have 2 windings and a core. Now, in your binder, the first thing they say is that there's going to be a high voltage winding and a low voltage winding, and that there's going to be a core. More often than not, that is correct, but there will not always be a high voltage and a low voltage. We do have what's referred to as one-to-one transformers as well, which are going to have the same value of voltage in as the same value as voltage out. If we've got one of those type of transformers, we'll be using that for electrical isolation, where we just want to make sure that we don't have anything pass from one circuit over to another. Once again, third year, we're going to talk about those a bunch when we're dealing with our variable frequency drives and with filtering, because that's one of the predominant uses of a one-to-one type of transformer. Most other cases, though, we are going to go and have a high voltage and a low voltage winding. Those are identifiable. Now, the high voltage winding does not mean primary winding. Okay, this thing could be high voltage or low voltage. Same as my secondary, could be high voltage or it could be low voltage. Actually, wanted to reverse that. I'll just call this low voltage or high voltage. Meaning that I can go and use this transformer, it's nothing more than a tool, to go and convert down from a value of voltage. I could come from a high voltage in to a low voltage out. That would be a step down type of application. Or alternatively, I could go from a low voltage in to a high voltage out. That would be a step up type of application. Primary does not refer to the voltage class. It just refers to the side that we are feeding in the power from. Secondary refers to the side that we are feeding to our loads. The high voltage winding and low voltage winding are identified in construction. High voltage winding is going to have many more turns. They're going to go and be thin wire. So HV. It's going to go and have many turns. The wire itself is going to go and be thin because the higher voltage side carries fewer amps. It's at a higher voltage, therefore it's going to be smaller, less amps. Thin wire. And it's going to go and have thicker insulation. Thick insulation. A low voltage side is just going to be the opposite. Anytime that we've got the low voltage, we're going to have few turns. Right, ampere turns. We're going to go and have thick wire because it's going to have a lot of currents. So it's going to be thick wire. And we are going to go and have thinner insulation. It's at a lower value of voltage, therefore it's going to go and have thinner insulation. Now, in a lot of places, you can't actually tell the insulation from one side away from the other because, if it's a 600 volt transformer, we'll just have everything that's going to be insulated usually to 1,000 volts or something like that. But in some of our high voltage ones, we definitely can tell the differences between the high voltage side and the low voltage side off of the insulation. The core itself is going to go and be made up of laminated pieces of iron. The reason for the laminations is to go and cut out any sort of circulating eddy currents. We know that we do have flux lines inside here. Those flux lines are cutting through here. If we're going to go and use iron, we want to use iron or something like that, so it's going to be a high permeability and a low reluctance. Permeability just means the number, or it's the efficiency of the lines of flux that it can go and fit into it. And then the reluctance is like how hard it is for it to go and stick those lines of flux in. One just talks about the volume of lines of flux, the permeability. One talks about the resistance of lines of flux, the reluctance. So we want to have a high permeability, low reluctance. We also want to go and have low retentivity. Retentivity is going to go and talk about how much the magnetic domains inside there are going to go and dissipate power when they're going to be changed. We know that every ferromagnetic material has got magnetic domains, which are physical components that get aligned when placed in the presence of a magnetic field. This is why you can take a magnet, put it on the end of a piece of iron, and then all of a sudden that piece of iron is magnetized, right? So all those domains, I've drawn them over here just being little V's or triangles. When we go and apply a magnetic field to them, they're all going to go in a line. They're all going to go and point in the same direction. However, the retentivity of a material is how hard it is for it to go and bend it. These are physical components. You can actually see them under an electron microscope. Look them up on Wikipedia. It's kind of cool. Look like little tiger stripe sort of things and stuff. But those actual magnetic domains are going to go and dissipate resistance, because as they have to get bent into alignment over here, they're grinding up against each other down at a molecular level, which means that there's going to be heat dissipated from it. We don't want to have a lot of heat, so we want to have fairly low retentivity. Low retentivity just means that these things are not going to retain or lock up. That means that they're just kind of free to swing around back and forth as we change the magnetic field. Last thing that we want to have is high electrical resistance. High electrical resistance is going to cut down on my eddy current that I'm going to go and have inside there. Now, we don't have any perfect materials, so we're going to go and have to, give up some in order to accomplish others, etc. Usually, our best materials are going to be stuff that is going to be iron-based. Silicon steel is like one. The silicon inside there gives it a higher value of resistance. The steel has got a fairly high retentivity, but it's not too bad. And the permeability that's going to be inside of it is, pretty good as well. The other thing that we do with our cores is that we are going to go and cut them into laminations. And the reason for that is that anytime I get voltage or flux lines, Eg is equal to BLV, I also get voltage generated, right? We get magnetic flux, we got length, the iron core itself, we got velocity, the AC moving in and out. Therefore, we're going to go and generate values of voltage. And those values of voltage are going to go and set up circulating currents inside of here that are just going to be called eddy currents. It's all based upon imperfections in the steel, whatever path it's going to go and take. Now, those eddy currents are going to go and operate in all sorts of axes. And so what we do, rather than having eddy currents up here and eddy currents over here, what we're able to do is we take the transformer core, we slice it apart into a bunch of different pieces, and then we laminate in between them. And what that does is it just prevents us from creating large eddy currents like that. We can still get them in this plane over here, but we can't get them across there because we're insulating between those layers. It's also a constructional feature for building the transformers. In a lot of cases, our transformers are going to be wound around thin plastic bobbins, and we don't want to have the core around there because it would be really hard to go and wind this around, right? You'd have to be passing a loop through here. Usually what's actually happening inside of our transformers is you're going to go and see welded joints in a lot of your transformers where they would have gone and created this winding just as a loop off of a machine. Build it as a loop. They'll just run it as a loop around a square form, and then all they do is they take this, which would be formed like a C shape and a flat bar, and then they just shove that through there, and then they weld across the bottom. That's why you're going to see those joints across there. There is a little bit of an error inside of your binder here again. They talk about, there's 3 bullet points. The first one on permeability that they talk about says, the higher the permeability, the greater the number of flux lines created for a given level of current in the windings. This is 100% incorrect. The current creates the flux lines. The core permeability does not. What you should be doing is replacing that word created with the word carried. The higher the permeability, the greater the number of flux lines carried for a given level of current in the windings. In other words, the higher the permeability, the more flux lines that we're going to go and force through the core, rather than getting what's called fringing, where we're going to get some that are going to go around the outside like that. If they go around like this, obviously it's not going to cut this winding over here, so we lose that little bit of transformer efficiency. The rest of them are, good to go. The retentivity, the resistance that they're going to go and have as well. The resistance one does make a difference as well because it is I squared R. So if we go with the higher value of resistance, we are going to have less watts of heat that's going to be dissipated by any circulating eddy currents that we're going to go and have inside of the steel. All right, let's talk about transformer efficiency. Efficiency is always going to be my output compared to my input. We know that there's going to be losses on transformer. If you've worked around one of these before, you have probably felt, just a small amount of heat coming off. They're wonderful places, inside of electrical rooms. You see people drying their boots on top of them all the time because it's a nice gentle heat, but it is definitely consistent heat. Transformer efficiency is going to be that power out divided by my power in. What's the difference between power out and power in? Well, we know that VAN is going to be equal to VA out for the most part, right? We know that, but there is going to go and be, before we even get to the input that we're carrying over from one side to the other, we are going to go and have some losses. So what it is my power input is actually my output power plus the power that is in my losses. We've got all those shred losses that we are going to go and have. So anytime that we're looking at a transformer, if we want to figure out its percent efficiency, we need to go and figure out how much power it actually outputs, and then how much it loses. We add the lost power to my output, and then we divide the output power by that. All right, let's talk about nameplate information. CEC does go and give us listings of what we need to go and have on electrical equipment. We'll find some of that inside of Section 2. We find some of that inside of Section 26. You will find a bunch of that type of stuff on you guys' code for the week over here. Let's talk about what's going to be inside of here just on a basis by basis. The first thing that they're going to go and have is the kVA rating. Transformers are always rated in kVA. We never say them inside of kilowatts because then what do we do when we've got an inductive load, right? We've got a lot of inductive loads out there. So instead they say, look, we're going to put it in as kVA. How good of a power factor you're passing through is all the way up to you as the electrician. You could be passing through relatively few watts and loads of Rs, but you'd have, X amount of kVA, or you could be passing through a large amount of watts and a low amount of Rs and get the same kVA. Just makes it easier for them to go and write this without having to go and add in angle thetas, etc. It refers to the total kVA that the whole transformer can go and pass through. If I have got a split winding, so sometimes my transformer is going to go and have split windings, we're going to take a look at those later on, then what I'm going to do is I'm going to divide the kVA among all the windings of either side. So let's say that this transformer here is 100 kVA, and that the transformer is made up of, and we're going to explain the configuration that we're drawing here later on, but for now we just need to go and deal with this section. If I've got a transformer that has got a high side and a low side that look like this, we refer to this as a multi-coil transformer. What I would do is I would say that 100 kVA, this whole side over here is going to be good for 100 kVA, but each of these two halves is good for 50 and 50, which gets me to that grand total of 100 kVA that I'm going to go and have out of that transformer. We can then choose to, series and parallel. We're going to look at all of that stuff on our connections later on. There is also, when we look at the kVA, they're going to go and give us voltages, but they're not going to go and give us current. And the reason for that is the only thing that controls the amount of current delivered by a transformer is the load. If they put the current on there and then you hook up only, a small little load onto that thing, then it's not going to be pulling that amount, right? So it's going to be up to you as the transformer to be able to take that kVA, divide out your voltage, and figure out your amperage ratings from it. High voltage winding. High voltage winding is going to be identified by its size and shape, but more importantly, high voltage is going to be identified by the letter H over here. Anytime that we see an H on something, that is going to be high voltage. If it's 2 windings, it's going to have only 1 to 2. If it's 4 windings, it is going to have 1, 2, 3, and 4. It's just going to be H with a subscript, or in a lot of cases when it's printed on the transformer, they just call it H1. They don't bother with subscripting. If I have got a dual voltage, if I've got that same split type as what I had there before, I might have a winding that is going to go and look like this. 120, or a high voltage winding that's going to be 120, 240 might be my rating. And my low voltage winding might be a 1224. What this means over here is that my second one is always going to go and be the series connection. We're going to look at connections later on. But for now, I just want you to work with the letter S. It's like that snake sound, right? So letter S stands for second and series connection when we're looking at these ones over here. The very first one, the first voltage rating that I'm going to go and have on there stands for first. Another word for first is premier. So the premier or the parallel connection that we're going to go and have. Use the S's just to remember that the second is always the series connection that we would go and have for these. If we do have something like this, what we would have is, if that is got a split winding here again, I shouldn't have erased that one before, but that split winding, we said before we'd have the total kVA, we'd split it in half, so each side would be 50 kVA and 50 kVA. But then we can also take a look at the voltages. The lower value of voltage is always going to be the individual sections. So each of these sections would be good for 120 volts over here in the high voltage. Low voltage acts the same. We're going to have, once again, if we get split, the lower value is going to be what I would have for an individual, what we refer to as coil inside of that transformer. The higher value, the second one, would refer to what it would look like if I were to go and series those two coils together. Low voltages are also going to be identified with X's off of them. So high voltage is going to be my H's. My low voltages are going to go and be identified with X's. And they give you X1, 2, X3, and X4. There is two other H's and X's that we need to go and talk about. They don't lay them out inside of here, so you're going to have to make that note inside of there. XO and HO that we are going to go and have. These are going to be your identifications for any neutral point. If you're doing a transformer that is a 12240 or something like that, you can connect an HO to a high voltage neutral. You would connect an XO to a low voltage neutral that we would have. Okay, phases are going to be 1 or 3 phase that we are going to go and have. 3-phase transformers, you can buy them with all 3 phases inside of the same unit, or you can go and build a 3-phase transformer out of 3 single-phase transformers. You want to guess what you're going to be doing in third year? You are going to go and take all this difficult transformer theory we're going to cover yet, and then you're going to go and build 3-phase transformers using 3 single-phase transformers. Frequency. Frequency does have to be rated on there. Once again, if I change frequency of any sort of a component, right? If I've got a 50 hertz transformer and I put it onto 60 hertz, there's going to go and be a difference. Why? Because that transformer winding is a inductor. And we know that XL is equal to 2 pi FL. So if I had a transformer that had a certain XL, or value of resistance, based upon it being 50 hertz, and then I took that and I upped that now to 60 hertz, that would mean that this frequency value would be increasing, which would mean that the XL value of that transformer would be increasing, which would mean that I could carry less amps. For us, operating on a 60 hertz system, if you pick up a 50 hertz transformer, or you get a 50 hertz transformer that is sent to you by the piece of equipment that comes from Europe or Asia or something like that, you have to know that that 50 hertz transformer can put out less amps on our system. Polarity. Polarity is going to be a different thing than what we're used to. We're going to cover what transformer polarity is in the next one, but each transformer is going to be either additive or subtractive. And it just refers to an instantaneous value. We will look at that later on. It could be written as additive or subtractive, or a plus or a minus. Percent impedance is going to be a big one. Sometimes it's going to be written as just being percent Z. Okay? If you see percent Z on there, guess what? Z stands for impedance. That's the percentage sign. That means percent impedance. It is going to be critical that you find and understand this value for calculating fault currents, specifically for calculating interrupting ratings that you are going to go and have for circuit breakers. Because the fault current is going to be the maximum amount of current that could go and flow through your transformer under a fault. And then I'm going to use this. We'll cover the formula later as well. But that is going to tell me how many amps it's going to put out under fault. So I need to make sure that my circuit breaker can clear it. Everybody should be familiar with the fact that circuit breakers, are going to be rated for, let's say, 50 amps. But then they're going to have an interrupting or a fault rating of like 10,000 amps that they can go and interrupt. You'd want to make sure that whatever your transformer is, that high rating, the interrupting rating, could be broken by it. We're also going to need to use that percent impedance to make sure that we can parallel two transformers so that we don't end up overloading one. Temperature rise is going to talk about how hot this thing is able to get. They will get warm. We don't want to place them any place super hot. Like, some people mount them up high on a wall. If you mount them high on a wall in a boiler room, you're going to cook that transformer. Because the temperature rise talks about the maximum temperature above 40 to which the insulation may be continuously subjected. Just watch to make sure that you don't exceed that. Insulating oil capacity and type of liquid used. These are going to go and lead to a couple of factors. We've got environmental factors, the type of liquid, whether it's going to have PCBs, polychlorinated biphenyls inside of it, or whether it's going to go and have any other type of dangerous substances. We'll also want to know what the capacity is, because your transformer is going to be a pipe bomb. If you have got insulating oil, the reason we use oil is because oil is denser than air, right? If you take oil, you pour it out in pour a cup of oil out, it's not going to float up into the air, it's going to fall straight down. because it's denser than air, which means it's going to be more thermally conductive than air as well. So if I take a transformer and I put all of my windings, take a whole pile of windings over here, and I put them inside of a container, and then I fill that container with insulating oil, the oil does a couple of things. It blocks out oxygen. It keeps my insulation, a lot of these have got like a paper-type insulation in between. It keeps my insulation moist, and more importantly, it carries that heat to the edge of my transformer so that that heat can be dissipated. Heat always moves from areas of high heat to areas of low heat. The quantity that's inside of here is going to go and determine how big of an explosion it could have, and therefore how far away we have to keep this from people or rooftop vents or a bunch of other stuff. There's a load of code rules to do with insulating oil capacity. Weight, you're just going to want to know that so you know how many other apprentices are going to have to help you move that thing into position. By the way, pallet jacks are your best friend for moving stuff around. If your company doesn't have one, look around on Craigslist. Eventually you'll pick one up for like under $100. They come up on there all the time, and you can skid stuff around so easy with it. Model and serial numbers under the CSA designation. They're the ones who go and choose, which equipment is allowed to be used and which isn't. There has to be model and serial numbers so that they can be tracked, so they can make sure that this was something that was actually approved. Type is sometimes going to be written on there. They don't always write what the type is. If it's specifically for something, signaling only, then they'll put it on there if it's part of a specific system. You can't just go take any old transformer and put it into a fire alarm system. They want to use components that they've got full control over so that they know it's going to meet their minimum standards. Last of all, wiring information. Wiring information sometimes is going to go and give you it in words. More often than not, it's going to be drawn as a schematic diagram. They say voltage vectors as well. I don't know about that one. I've never yet seen a single transformer that has a voltage vector. I just think that somebody that's overly excited about vectors probably just got, wanted to throw that inside there. If you find one, send me a picture, because until I, have actually seen one with a voltage vector on it, I don't believe that they're actually out there. Usually they just show simplified versions of the windings themselves. All right, that's it for this one.